Cool, right? Oh, is it recording already? Oh, hi. I love physics in the summertime. We're going to talk about fluids as they flow through pipes in this case, and sometimes just open fluids flowing through the air. There's two kinds of fluid flow. One is called laminar or laminar, and one is a little bit of turbulence. Laminar flow, this is kind of a drawing of the side view of an airplane wing, or it could be a car as it drives through the air, but then these orange lines would be what you'd see in car commercials when they're in wind tunnels and they put smoke going through. Little streamlined flow to show how wonderfully aerodynamic something is. So if fluids flow nice and smoothly, there's no turbulence. I mean, that's the other kind. If it's nice, happy fluid flow, that's called laminar. What happens more often than not is you get a little bit of turbulence going on, and what that causes or is caused by is when air molecules slam into something, it's Newton's third law, they're going to bounce right off. And sometimes when it bounces off, those little air currents start to dance a little bit, and it's an irregular, not really right, but kind of a random pattern of where those bouncing off of air molecules end up going, and this can cause uneven density of air as this item flows through the fluid. And then in the back, it's also caused by fluid getting drawn into the region that that item has been plowing through. It leaves a little bit of a vacuous region behind it because this item is literally moving the air out of the way in front of it. And so as the air goes around it, it gets drawn into that region, slams into itself, and causes some uneven airflow behind there. But the fact that it's a little vacuous behind it is the basis. You've heard of drafting in race cars or in NASCARs when you get two cars like basically touching each other because they divide air resistance between the two cars, so they both end up going faster. But those are the two kinds that you're going to deal with. We're going to focus on, in this level of physics, nice, smooth, laminar fluid flow. And so what this is an inside or just a cross-section version of, imagine a water pipe that water is flowing through here, and when that pipe gets constricted, we're going to take a look at what is the mechanism for something you all already know. If you squish the end of a garden hose, the water flows a little faster. So we're just going to take a look at what is the physics behind that happening. All right? So first of all, we'll have to define a few parameters here. We're going to take a look at a certain quantity of water, a certain volume or mass. It doesn't matter because density relates the two. So if we want to focus on, say, this much water right there, we can define it with a certain number of parameters. One is the area of that pipe as the water flows through it. The other one is the length of that certain quantity of water, however much we care to call it, but it's just an area times a length, which you know then you can multiply together to get a volume. Volume is a capital V, and as it's moving, it has a certain velocity, which is a lowercase v. So you got a length, area, volume, velocity. That ought to do. Okay? Now, as that quantity of water flows through this pipe, it gets squishified. If you can envision then that same item, the area decreases and the length is going to increase. So that same quantity of water then might be drawn like this. And the joke I tell is it's skinnier, which is why it's fatter. So this length goes up, this area goes down, that volume has stayed the same, and the velocity has gone up. So I got a 1, a 1, a 1, and a 1, a 2, 2, 2, 2, even though the volumes end up being the same. All right, so we're going to take a look at what is it that causes that velocity, V2, to be greater than V1. All right? And what that's called is a mass flow rate. A mass per time is the flow rate, and that will stay the same. Okay? All right. First of all, mass. Well, there's another way to spell the word mass, and that's a density times a volume, because you know the density of the liquid is equal to the mass divided by the volume. And if I want to replace the mass, another way to say it is density times volume. So what I can do there is say we can talk about a density of the liquid times the volume per time. Density times volume per time is another way to say mass per time. And what do we say another way to say volume is area times length. So this is the same thing as the density of the liquid times the area times the length per a certain quantity of time of what's flowing through it. Another thing you all know is, hey, length divided by time is another way to say velocity. So what we can replace this with is a mass times area times velocity. Or I'm sorry, density times area times velocity. And that's of the liquid, and that's area 1, velocity 1. Okay? That is what mass per time is equal to. Now, if we keep track of that mass of water, that certain quantity, however many water molecules it is, it doesn't matter. That mass stays the same. If we say however many of those molecules pass by you in a certain amount of time, say a minute or a second, or in plumbing systems, they usually call them gallons per minute, doesn't matter. But then that time would be the same over here. It's just a certain quantity of water flowing through you per a certain amount of time. And so what we said already, what you can tell is, since the density of the liquid doesn't change, if this gets smaller, that has to get bigger. And so this this density of the liquid times the area at location 2 times the velocity at location 2, since it's the exact same liquid flowing through the exact same pipe, density doesn't matter, and so area times velocity is equal to area times velocity. All right? One thing we use this as an example of, just to make an application, is in biology, where you have blood flowing through certain arteries. And what they'll use with that is they'll usually say, hey, you got an aorta, that's obviously a larger section of the pipe. Then you got capillaries, which is the skinnier section of the pipe. And what we'd have to look up here, I don't know, let's say the aorta is 1 centimeter radius. Let's pretend in our headsies that the area, combined area of all the capillaries, is 2,000 square centimeters. Ish. Okay? How fast does the blood flow in your aorta? I don't know either, but it's dancing around ish 30, about a foot, centimeters per second. And so then what we'll find out is what is the velocity in the capillaries. All right, so first of all, you know the capillaries are skinnier, so it would make sense to think that the blood flows faster. But since you combine all of the areas of the capillaries, it's considerably larger, so the blood will flow slower through the capillaries, which makes sense because the whole point of blood flowing through capillaries is to exchange gases. The slower it goes, the more efficient the gas exchange is. Plus, it makes sense to have a lot more surface area, because again, that whole area, the whole point is to allow the fluids to, or the gases to exchange. Okay? So what we'll end up saying is the area of the aorta times the velocity in the aorta is going to be the exact same thing as the area of the capillaries times the velocity in the capillaries. I gave you a radius for the aorta and a velocity for the aorta, so we can put numbers in there. I gave you a combined area of the capillaries, so really the only thing we're going to look for is this one. The only thing to be careful of is centimeters per second, centimeters per second, centimeter radius. Velocity usually will go in meters per second. So it doesn't matter if you want to keep the numbers in centimeters per second or meters. Just make sure your units are going to agree. So the area of the capillaries, what do we got? It was 1 centimeter. So I'll go pi times 1 centimeter squared. So that's pi r squared times the velocity, which is 30 centimeters per second. And I'm going to divide that by the area of the capillaries, 2,000 square centimeters. Okay? And what will we end up being left with is that square centimeters kills that square centimeters. The pi doesn't have any units at all. This is just pi times 30 divided by 2,000. And the velocity ends up being ish 0.05 centimeters per second, which is ish, what's that, 0.5? No, I did that wrong. It's not 0.05. It's dancing around a half a millimeter per second, which means it's about, what, 0.05 centimeters. If that were, it'd be about 0.05 centimeters per second. But anyway, just to give you a visual, about half a millimeter per second is all the faster blood flows through your capillaries, which you don't want it to go very fast again, because you want the gas exchange to take place as much as possible. But anyway, the fluid flow equation is, again, the area times velocity is equal to the area times velocity. And if you want to again talk about mass, just multiply it by density. If they want to talk about kilograms per second, if they want to talk volume, then you can again take the volume like gallons per minute. You can divide both by mass and get back to a volume per time. It's always going to stay the same. So the fluid flow equation, and then this is going to be the basis of the next video, which is Bernoulli, and the joke I say about him is that guy blows. But anyway, yay physics.